Hello everyone, and welcome to another webinar co-organized by ENT Neuro. My name is Beatrice, and I'm a product manager of Neurofeedback and QEEG solutions at ENT. And today I'm glad to be hosting the webinar on Brainmaps and Neurofeedback, a smooth workflow for individualized training, which will be presented by Dr. Philipp Heiler, who founded his medical practice in 2016 and is specialized in EEG, QEEG, and neurofeedback. Over the years, he has worked with hundreds of patients and he's collaborating with the excellence universities of Munich. To improve diagnosis and treatment of his patients, he founded the company called BrainBoost to develop the neurofeedback software called BrainAssistant and use innovative technologies like AI to learn more about the human brain. This is going to be a highly interactive session with a combination of scientific and practical content. There will also be an expert Q&A panel at the end. In the course of the webinar, you also have the option to type your questions, which will be addressed at the end of the session as far as the time allows. Like most of our ENT webinars, you will also be exposed to some poll questions, which will be appreciated if you take part in them. So, Philipp, once again, we appreciate you accepting our invitation, and we are looking forward to learn more about your research and work.
Thank you very much. Thank you for having me. I'm happy to be here, and I hope that this webinar will be informative and also a bit fun for those listening in. I will go over some slides with some background about neurofeedback and brain maps to make sure that everybody knows what we're talking about. And some of the things I will present will also be maybe, or will leave room for discussion. I think we still have a lot to do learning about brain maps, learning about neurofeedback. So I'm presenting you the way that we currently use, but I will also give you some outview of what we are working on and where we hope to improve the process. As Beatrice said, if you have anything in between, feel free to type in the chat. And I hope that right now you are seeing my slides. So you should see my screen that says brain maps and neurofeedback. So I hope that's the case. And then I will start with the presentation. If this is not the case, please make sure to write in the chat and then somebody will let me know. All right, first of all, I want to make a little disclaimer. Potential conflict of interest, maybe. I am involved in the development of the BrainAssistant. So the BrainAssistant software that I will use screenshots from and that I will also use later for the live demo is the software that we as BrainBoost actually develop and that we develop also in cooperation with my medical practice that is completely specialized on neurofeedback. However, the things I will talk about today can be done with any or some other EEG and brain mapping softwares as well. So I think the knowledge that you will receive is not dependent on being a user of the BrainAssistant. Also, we are working together with ENT Neuro. So we're using amplifiers from ENT Neuro and we also resell them, but we also work with other equipment as well. So also here, I would say I will present something that you can do with any other hardware in the neurofeedback field as well. So hopefully it's fine and not too much tailored to a specific tool or hardware. All right, let's talk about neurofeedback. And this will be the first test if the poll feature is working well and if you guys are actually listening. So as Beatrice mentioned in the webinars, we have the option that I ask your opinion or questions to the audience. We will have 4 questions, so you don't have to get too active. And the first question, I will read it out and then you will have the option to pick one of the answers. I'm not sure how exactly it will work, but somebody will take care of it. So the first question is, do you know what EEG-based neurofeedback is? And the answers are, yes, I have exposure to neurofeedback on a regular basis, either practicing it or having a colleague that practices it. I'm familiar with neurofeedback, but I do not work with it on a regular basis. Or C, I have heard of neurofeedback, but have no practical experience. Or D, I have never heard, sorry, spelling mistake, I've never heard of neurofeedback. Okay, so now let's see if it works. If you could try to please start the poll feature so that people can vote for the answer that they want to pick.
Poll is out now.
Okay, nice.
Will you wait for a few more seconds? We're closing the polls now. And this is the result.
Okay, let's see. It's very small for me, but I can see that some said, yes, I use it on a regular basis. And then some more said, I'm familiar with neurofeedback, but do not work with it on a regular basis. And then the majority said, I have heard of neurofeedback, but have no practical experience. It's roughly, almost 50%. And some people say, I have never heard of neurofeedback. All right, that's good. So most of you have heard of neurofeedback and some haven't. So hopefully for everybody, you will learn something new today. So now, can you switch back to my screen? Let's make sure this works. Okay, looks good. Okay, so what is neurofeedback for those who are not familiar with it? The idea of EEG-based neural feedback, I usually explain it to my patients like that, is to help people, patients or clients to train specific functions or specific skills of their brain. To enable them to do that, we use a live EEG recording. Usually we do not do a full cap EEG recording for neurofeedback, but instead we pick a few channels that we want to work with. So we do, every time people come here for a session, we do an EEG recording of one or several channels, and then we monitor the EEG signal in real time. And now there are different forms of neurofeedback. Some are based on the frequency bands. This is also what we will mainly talk about. Some are based on other EEG features that are used for neurofeedback. But there's a real-time analysis of the EEG signal. And then we decide what we define as a desired or positive state. So let's say we want to help the patient learn to be more focused. Then we would say, okay, focus is usually associated with a high amplitude or a high power in the beta frequency band and not too much power in the theta frequency band. I'll get to it in a second. And then we say, okay, if the person manages to suppress theta and increase beta power, then we want to show this as a positive reward, as a positive feedback. And if it goes the other way around and the brain is drifting off, then we want to show a negative feedback or a negative results. And now we have to find a way to also transport that to the training person, the patient or the client. And we usually do that by showing them a little game on a screen. So in the game, the little character will fly up whenever the positive feedback is given, and it will drop down when we want to give the negative response for the person. That's why it's called neurofeedback. People will receive feedback about their brain activity. So we are creating a closed loop between brain activity and feedback about that brain activity. And the idea is that via reward-based learning and also at some point skill-based learning, the patients can learn to have more control over their brain activity and thus also improve their symptoms. That's the idea of neurofeedback. Since it is basically a training process, it usually takes frequent sessions. So we can do 1 or 2 sessions every week with a total of 20, 25, 30 sessions, depending on the case. That's what we are specialized in. So we deal mainly with, we have kids, teenagers and adults, mainly with ADD and ADHD, but also some with depression, anxiety, sleeping disorders, epilepsy, migraine. So I would say all kind of mainly psychological and some neurological conditions that people come here. I would say we usually have a good success rate because we also try to do, let's say, expectation management and do not promise too much. and we do an assessment process to figure out if the patient will most likely benefit from neurofeedback or not. And we will also do an assessment process that helps us pick the right training protocol. And this is exactly what I will present to you today, and show you some tools that we use to figure out if this is a good case for neurofeedback or not. As I mentioned, the neurofeedback is usually done on one or several channels of the EEG. So we usually do not put the full cap on patients every time for every session. We usually have adapters that use touch-proof electrodes and, for example, do a minimum configuration of a one-channel recording, which could be a ZZ recording. In the neurofeedback field, we usually use a reference on the earlobe or on the mastoid bone. So we have a reference electrode, and we usually have a ground electrode. So if you want to use that with amplifiers that come with a plug for caps, for EEG caps, then we usually have an adapter that gives us several options for individual touch-proof channels. And this would be the minimum configuration for neurofeedback. The neurofeedback training on the position CZ is something that is very commonly used. There are actually some practices that only do neurofeedback on CZ. And in the German S3 Leitlinie to treat ADD or ADHD, we also find the recommendation to work with the ZZ SMR training on the position, on this position with the patients with ADD and ADHD. What does that mean? I mean, if you are familiar with neurofeedback, then this might be clear to you, but for those who are new, I would explain what it means. I hope you do all have some knowledge about EEG. Generally, we can say that if we have a raw EEG signal, we can split it up in different frequency bands. So we filter the EEG signal for different frequency bands, and then we can see the band power in a specific frequency. So for example, when the brain is asleep, deep sleep states, we would expect higher power, like a higher amplitude in low frequency bands like delta, because the brain cells are not sending a high frequent amount of information. So they're synchronized in slow wave patterns. And if we are very active or focused, we would say that the EEG is desynchronized, and that would show us higher power spectrum in faster frequencies. The frequencies have names. They are named with these Greek letters, basically, in a little bit of a confusing order. So these go actually from slow to fast. So for a typical neurofeedback training, amplitude-based training, we pick certain frequency bands that we want to work with. For example, in this case, we have 4. We don't work with the full EEG spectrum. We pick 4. And usually every frequency band has a direction that we would like to move from a power point of view during the training. So if we want to teach the brain to be more calm and focused, we usually don't want too much power in the theta frequency band. So we want a lower amplitude of theta frequency. So this is why the arrow is pointing down. And we usually also want a lower frequency, a lower power in the alpha frequency band. So this is why this arrow is pointing down. The SMR is a sensor motor rhythm. So in the field of neurofeedback on the position CC, there are some studies that show that increasing the power of this frequency band, which ranges from 12 to 15 hertz. So it's basically the low beta frequency band. Increasing the power in this frequency band can create a good level of focus and calmness, emotionally as well as physically. So we're trying to increase the power in the SMR frequency band. And for the high beta frequency band, we are trying to decrease the power because we do not want to create over-arousal states of the brain. So we have basically an assortment of different frequency bands. We have a specific position that we work on. We have certain training directions, and then we monitor the real-time EEG and decide whether or not a certain condition is met. So we usually put a threshold at a certain level for the patient, and then we can decide if the positive reward should be given or not. Another example for another kind of protocol would be this. Very typical protocol is the alpha training. So it's usually done with eyes closed, and there is some, I would say, neurological studies that show that increasing the power of the alpha frequency band in the parietal or occipital region of the brain can help people enter a calm and relaxed state. So usually we use this protocol to help people learn to relax and calm down. So we would position the electrode on a different position, PZ for example. We would still try to inhibit theta to avoid people drifting off and falling asleep. We would try to increase the alpha power. So for example, we could split alpha in lower and higher alpha, or we could do just one parameter for alpha to increase power in alpha frequency band. And similar to the protocol before, we want to decrease the power in the high beta frequency band. So that's usually the idea of neurofeedback, to have a certain position or several positions, and then have certain frequency bands that should go up or down, and then use a combination of these. And then hopefully the patient can learn over time to control these brain activities by themselves, either in a subconscious way or even tying them to certain mindfulness exercise that are then linked to the neurofeedback. This is another topic that I will not dive into too deep today, but this is something we do as well. So the big question is, and this is a topic that is a little bit tricky, and it will take 2 seconds until you can see the slide, how to pick the right protocol. And this is something where I feel like a lot of manufacturers in the field of neurofeedback have tried to create a very sophisticated mechanisms to try to make the neurofeedback more customized, or look at least more sophisticated. But it seems that sometimes this was going the wrong way and was over-engineered and basically did not have a better outcome than we had with the default protocols. So full disclosure, in the German Leitlinie, it says you should stick to the default protocols and not go with a QEEG-based protocol, at least not a Z-score-based one. We still use the QEEG to check for the likelihood of success, but you can all figure out if this is a process that you would like to implement yourself. But I'm saying this, it's a long time I've also worked simply based on the clinical analysis of the issues of the patient and then picked the neurofeedback protocol accordingly. But now I of course appreciate at least to have the option to look at QEEG data. So QEEG I rather refer to, or let's say, brain maps. Brain map basically is a form of visualization of EEG data. We'll go into detail what kind of brain maps there are. But first of all, I want to give this question to you to see how much experience you have with brain maps. So my question is, have you used brain map visualizations for EEG data at all? Not related to neurofeedback, but generally, do you use that? A, yes, it is part of my regular routine. B, I'm familiar with them, but I do not use them regularly. And C, I have never used them. All right, now please go ahead and start the next poll.
We're about to close the poll. This is the result.
Okay, so some say, sorry, I have to get closer to the screen, but it's fine. Some say, I think like 50%, yes, it's part of my regular routine. Then there is some 30% saying, yeah, I'm familiar with it, but I do not use them regularly. And C, I have never used them. So hopefully for you, it will be interesting today to see what kind of brain maps there are. So please return to my screen sharing. Yes, perfect. So what is a brain map? Let's take a look at what a brain map actually is. So I would say every brain map needs the following. It needs to tell us what kind of EEG parameter it is displaying. It can, for example, be a frequency band. So this brain map displays the power of the alpha frequency band, which consists of 8 to 12 hertz. And then we usually need a certain EEG segment that the brain map is working on. So let's say you record an EEG of 5 minutes, and then you select either the full 5 minutes, or you select just 1 minute of your EEG file that was, for example, recorded with eyes closed. And then you say, give me a brain map of the alpha power of this segment. There are other ways of brain maps, but let's stick with this for now. So I have the alpha power of a specific EEG segment. And instead of looking at all the raw EEG lines, I use the data, average it, and then I can create a brain map. On the brain map, you will find the recording position. So this is a brain map according to the 1020 system. And so we use the data from every channel averaged, and then we draw a color map that shows us the alpha power in this segment over the positions. So I would say it's easier to see for the human eye the distribution of the power, and also to get an idea of the power, of the level of the power. But of course, it kind of hides the time that we are looking at. So if we are doing one brain map for a 20-minute EEG, it will always give an average of the 20-minute EEG. And this is one disadvantage of static brain maps, that we will always see only a certain time period. This is why we usually do several segments and generate several different brain maps for these segments, and I'll get to that in a second. And then usually a brain map should have a certain scale that shows you what's going on in that brain map. So here, for example, the scale is adjusted to some minimum and maximum alpha power values, and we can see that there is the highest power of alpha is on the position C4 and some on the position O2, while we do have the lowest values on the positions T5 and T6, or P7 and P8, depending on which naming of the positions you use. And for example, this would be another brain map displaying the mid-beta. This is just a general idea. So brain map takes EEG data over a certain period of time and makes a graphic visualization of that. And this can be used for different parameters. And I will explain some of the parameters to you in a second. What is usually our workflow that we go with when we have an assessment here for neurofeedback? So I want to toss that in so you understand where the brain maps come into play when we see patients. So usually in the first session with the patient, we want to collect as much data as possible to assess if neurofeedback makes sense for them. So we usually start with an open interview with the client. That's what I like to do. Ask open questions, get an understanding of their symptoms, of their sleep, of their family history, and so on. So I basically do a psychological interview with them. And then we have this feature just new. We also do some questionnaires to see how do they rank on a standardized questionnaire. So for example, for a depressive person, you could use the BDE or PHQ questionnaire. So some screening questionnaires usually do get an understanding also of their symptoms. And we also, that's also a new feature, I will show you later the results. We also do some cognitive tests. So we have a battery of 6 cognitive tests that we can do with the subjects. For example, a go, no-go test, or a Stroop test, or a finger tapping test. And we also have a memory test, the Corsi, and things like that. So we also do some cognitive tests with them. And then we actually proceed with the EEG recording. So we check for impedance and signal. And then during the recording, we usually have automated flows that will generate specific segments of brain maps right during the recording. I will show this to you later in more detail. Then we can generate brain maps according to several segments, and then we generate a report. And in that report, we also look for specific scores that are usually parameters that are connected to at least giving you some idea about the potential neurofeedback outcome. I will go over some of the scores later with you as well. So we're not only looking at the brain maps, but we're also giving out some scores to see if there is some targets for neurofeedback. And then usually in the first session, since the people are already here and have the cap on and have an EEG running, I usually pick a neurofeedback protocol and give them a first view on neurofeedback and how it works, usually in one go. And for the following sessions, we usually start with a brief interview, but then we usually skip all this and go right to the neurofeedback part of the session. We are trying to establish now a routine where, for example, every 10th session, we will do the full assessment process again to have options to monitor progress for the patient, but right now, well, this is what we're doing right now, but this is usually our full assessment workflow that we go through with, and we wanted to have a software where we can do all this at once. So talking about brain maps, there is maybe some confusion, and I want to talk about this really quick because I think it's important. So some people associate brain maps or QEEG in general with Z-scored brain maps. So when we look at a regular brain map that is, for example, displaying us the alpha power, we might run into the problem that we have no idea if what we are seeing is good or bad. I mean, of course, if you're an experienced neurologist, then this might be something that you should know. But generally, brain maps that just display EEG parameters, they might look very confusing. Because, for example, some brain waves might have higher power spectrum on a different position of the brain. So it might look like this very colorful brain maps, a lot of blue and red and all colors, and we don't know what's going on. So the general idea of having a database that I could compare brain maps to and then see, is this brain map close to what we expect for a normal brain? And I want to put this in parentheses. You know, this is what's currently happening, to say, hey, let's compare this brain map to a normal database, normative database, and then let's see what it gives out. And then we will get a view that looks more like this. So the Z-scored brain map will only show me the deviation from a normative database. So I toss these brain maps in there and say, hey, if the value that we can see, for example, for alpha, or let's pick a better one, delta is good. If the delta values from my brain map look like they look in the normative database, then please color the brain map green and show me there's a range of, let's say, plus minus or around the 0 Z-score. So there's no standard deviation from what we would expect to happen. This makes it, of course, easier, especially for beginners, because then we will see a green brain map and know, okay, this is as expected. If there is value, so for example, in this case, this person seems to have higher values in their theta power. So this is why the Z-scored brain map is colored red. It shows that the theta values of this person are way above what we usually expect in a normative brain map of a person of that age and that sex. And according to the other ones, these ones are a little bit blue, so that means we have less high beta power than we actually expect from a person of that age, of that sex and gender. And this already shows you the problem that we can have with databases and brain maps. I actually did write a chapter in a Springer book about ADHD and neurofeedback, specifically about Z-score based neurofeedback and Z-score based brain maps. So I did extensive research on the topic, and while it sounds very interesting, there is not a lot of research actually backing the idea of saying, hey, let's only do Z-score based analysis of brain maps, and then let's only do Z-score based training during neurofeedback. Which would basically just pick the deviant Z-scores and train only them and try to train them closer to the 0 Z-score of the database. But I understand that it is interesting to have a database that is, showing you is this expected value of what I'm looking at or not. So we also created a database based on data sets that we collected. I'm not telling you how many data sets we have because I first want to run the next question with you to see what you think about it. So I hope the idea is clear. Let's do 3 more examples to see what kind of brain maps we can expect for basically the same parameters. So now we're looking at the absolute alpha power. So we're looking at an alpha power, and here I have brain maps that adjust for individual minimum and maximum per, sorry, not alpha, it's absolute power of different frequency bands. So here we have brain maps that adjust for the min and maximum of the power in the specific frequency band. So this will help us to find minimum and maximum locations of this power. So for example, it shows us that we have on the position C3 and C4, we have a higher alpha power than in the surrounding areas, and we also do have higher alpha 2 power in the O1 and O2 position, for example, and we have a higher mid beta power in the frontal lobe and so on. So this gives us an idea about where is the per frequency, where is the minimum and the maximum, but it makes it hard to compare these brain maps with each other because, for example, while the theta brain map goes up to 500 microvolts squared, we can see that the mid beta brain map is only going up to 20 microvolts squared. So we have totally different min and max scales for these brain maps. So we can also do a setting where we have a unified scale. So here we pick from all the frequency bands combined, we pick the minimum and the maximum. So it makes it easier to compare the frequency bands with each other. So this is the same recording than we saw before, but here the scale is the same for every brain map. So the advantage is that we can compare the frequency bands to each other more easily, but we lose contrast, for example, in the beta frequency bands, which are much lower than theta and alpha. So this means here we can get an idea of which is dominant frequency band in that recording, but we lose details for some of them. Of course, this is adjustable in real time, but still. And then we have the z-scored brain maps, which are nice to look at, but again, here also we lose details about what's the true value of the parameter. So here we just get the z-scores for the absolute power without any knowledge what the absolute power actually is. It's just picked from the normative database, and we can see, okay, theta and alpha 1 seems to be somewhat deviant from the normative database. So next question for you, because this is where it gets interesting, is, let's see, when it comes up, I can see you. Okay. How many EEG data sets do you expect to be included in commercial databases for z-score brain maps? So this is just your gut feeling. Like if you have a normative database that you are comparing EEGs to different ages, different sex, how many z-scores would you expect to be in these databases? What do you think? Where would you feel comfortable using these databases? So let's see. Yep, perfect.
It starts now.
Sorry, I can see the last one should say less than 250, not more than, of course, it means less than 250.
Closing the polls now. This is the result.
Okay, let's see what you think. I don't know if somebody knows. There's like, okay, so we have a quite even distribution of, let's say roughly a third that says 2,500 to 5,000. Then we have a third that says 1,500 to 2,500. Then we have some that say a third that says 750 to 1,500. And then we have only 10% saying 250 to 750 and another 10% roughly saying below 250 or more than. I'm not sure how you read it, but let's just say the majority would expect this database to have quite a bunch of data sets. And if you go back to my slides, thank you very much. This kind of like makes us run into, or this is a tough one, because there are some commercially used databases out there, and we in the BrainAssistant also offer a database based on recordings we have right now. We specifically explain that this is an empirical z-score database, so you should use it as an add-on to what you are doing with your brain maps, but you should not base your decision only on the z-scores. They can be used to confirm your decision, because our database currently consists of roughly 600 data sets. So we are in the lower half of what you would be accepting. But most other commercially used databases that have been around for quite some time only also have either NeuroGuide is probably the most famous one. They do have a roughly 700 data sets. And then QEEG Pro, which is a newer one, they have about 1,500 data sets. And the problem is clear, because if you actually say, okay, we have to filter for sex. So if you have a female, then you have to toss half of the data sets out there already. So you're down to 350 data sets. And then you say, okay, I have a certain age group. And if you say, okay, 50% of the data sets that are used for kids below 18. So I will toss them out if I have a 35-year-old. So I'm left with only, let's say, roughly 170 data sets to work with. So this can get narrowed down quite quickly to only a few data sets. So I agree with you. We need to work hard to grow these databases and get them to numbers that are above 1,500, above 2,000, above 3,000. This is also what we are trying to do. And this is why we build a dynamic system to add more and more data sets as we go and make sure we select data sets that are of high quality. So I would say this is an important topic to work with. So I'm glad to see that you also agree that we need to put in some more work to get more data sets in. All right. So the EEG recording workflow. So I just want to briefly go over this because I can see that time is running. So we usually do, as you can see here, a screenshot, because if you don't have too much time for the live demo, that's fine, because you can all download the software for free and give it a try. But here you can see what we usually do. So we have an automatic flow that records several segments of EEG data, and they are usually color-coded to understand which segment is which. So for example, we have a baseline recording of 1 minute. We have a first eyes open segment of 3 minutes. It's a resting state, eyes open. Then we have an eyes closed segment, resting state of another 3 minutes. And then we have 2 interventions where we do cognitive tests while we do EEG recording. This will lead to more artifacts, yes, but we still want to be able to see if we can find something interesting in the EEG data during the test. So for example, with the Stroop test, people have to push buttons and pick the right color that matches the word that the color is written in. And then we have another eyes open segment for 2 minutes and another eyes closed segment for 2 more minutes. So this will then give us a lot of data, a lot of brain maps, and this is why we usually could not process them all and have created an automated report feature that will look for specific scores in these brain maps, and this will be the last topics that I will go over today. And this is something we actually we are doing research on, for example, with universities in Munich, but also in Heilbronn, to find better scores, parameters that we can use for different pathologies to understand if the pathology, for example, ADD, which parameters is it actually linked to, which ones can we look for. So we now have implemented 12 parameters that are, let's say, that at least have some literature that backs them, but we still need to improve the evidence grade of the parameters that we use within the segments. But this is what we're doing right now, recording a variety of segments and at least have a look at what we find in there. Yeah, I mentioned this. What we already do is that we, for example, do also clinical tests. This is the outcome of or a typical outcome of the go, no-go test. People are presented on the screen with either a circle or a square. When they see the circle, they should push the button. When they see the square, they should not push the button. And here we can see, okay, he had 80 in total shown, 40 where he should press, he pressed, so that's good. And no, sorry, he had 40 where he should press and 40 where he should not press, and he pressed at 48. So we have a commission error rate of 8 that should not have been pressed. So there is an impulsivity level that comes with ADD or ADHD, and this means we can see that there is a commission error rate of 10% basically. So we also include these tests when we do the assessment. I will actually skip the 4th question because I think it's not so important, and I want to get to the scores that we look at so that you might get some understanding of what we're looking for when we are trying to determine neurofeedback. So these are the scores that the report will actually generate automatically for you. And the cool thing is that it automatically picks the right segment. So if you're following the flow, it will make sure that there is an open, eyes closed segment, and so on. So what we're looking at, very typical neurofeedback parameters, is the theta relative power, or the theta-beta ratio. Now, there is some research that suggests that maybe the theta-beta ratio, especially in ADD or ADHD, is maybe not as reliable as we thought that it is, but it seems that most trainings are still done either being theta stop beta go training or an actual theta-beta ratio training. So we have two parameters looking for excessive theta, especially in comparison to the beta power. We also look for alpha, excessive alpha, especially with eyes open, because it seems that in some kinds of ADD or ADHD, we do have excessive alpha activity. So we're looking for this. So this is actually the score of the case that we just looked at, and this matches the Z-scored brain maps. We do have excessive theta as it looks like. So we have a red signal that indicating that these could be good targets for neurofeedback, but the alpha does not seem excessive. So we do not have a flag here. It's green and says alpha is probably not the best target for neurofeedback. And then we have the ratio of alpha 1 to alpha 2. So we usually expect alpha 2 and alpha 1 to be slightly or roughly balanced. Here we have more alpha 1, lower alpha 8 to 10 hertz compared to the higher alpha, which is 10 to 12 hertz. So here, this is also a potential training for neurofeedback. And this is actually, I would say, compare or next to alpha trainings and SMR trainings. This is, I think, one of the trainings that we could actually see some research on that shows that it's promising. So this could be an indicator as well. Arousal score checks for the high beta to beta ratio. So this seems not to be a brain that is over aroused in any way. It seems to be rather under aroused with a high level of theta. We look at the sensor performance. That means we look at the parietal cortex and see how the alpha distribution is in the parietal cortex. So this seems to be a promising field as well. We look at the mu rhythm, so excessive alpha on C3, C4. This was a little bit high for this patient, but not excessively high. We look at the frontal alpha asymmetry. This was also not flagged, so it seems not to be too prominent here. We look at the increase of alpha from eyes open compared to eyes closed. So for example, this is a parameter that will use different brain maps and take them into account. But in this case, we have an increase in alpha power of 46%, so this is as expected. We look at the theta to alpha ratio with eyes closed. So here we see a little bit excessive theta with eyes closed, which fits the general level of under-arousal. And then we can see that we look at the distribution of alpha from frontal to parietal lobe. This is also slightly flagged. And then we look at for excessive delta and excessive or artifact score as well. But this seems to be okay. So the last two are more like an indicator of how good your EEG actually looks like. For all these scores, we actually, in the report, we generate a full page that will then give you some more details. We are very transparent with what we do. So if you're using that score or the reports in the BrainAssistant, we will write exactly what we calculate and how we calculate it, so you can figure out yourself if this is something you would like to use or not. And then we give some more detailed brain maps. And this is basically what we do with all the scores that are relevant for the clients. I will not go through all of them again, because you can sorry, just checking the chat. Sorry, just seeing if there's something relevant. So this is what we usually do for the 13 parameters. And as I said, our goal is, and this will also be involving a lot of machine learning processes to understand better which are more reliable parameters. But right now we put together the interview with the patient, then the cognitive tests, then the brain maps that we create, the scores we create, and then we pick a neurofeedback protocol accordingly. And so I think I was taking up a bit too much time for the theory, but I think it was important to make sure that all of you understood what I'm talking about. So I don't know if there are any questions yet, so we could get to the questions. Otherwise, I can also squeeze in 5 more minutes for a quick demo of how the BrainAssistant looks like. But there is also a demo video out there that we recorded, Beatrice and I. So there's also always the option to watch the demo, and there's also a free test version for 14 days, so you can just download it and also go through it yourself. So I'm leaving this up to the organizers. Beatrice, what do you think? Should we do 5 more minutes of the demo, or do you want to go to questions?
Thank you. I think we can do 5 more minutes, so you can show a bit the BrainAssistant software, and then we can switch to the Q&A section. Thank you so much. Okay, perfect. So sorry for talking too long, but there's always so much I want to make sure that you guys hear. But if there's something
unclear, feel free to contact us anytime. You can just, or Beatrice, of course, and the team of A&T Neuro, but you can also contact BrainBoost. So looking at the BrainAssistant, just so you get a feeling of how we can work with the brain maps. So looking at the BrainAssistant, we can usually, we just log in, and it's a little bit delayed, but I will click slowly, and then we can pick a client to work with. And if we already have an EEG recording, we can just move to this session, and then we can go to, we can open up the EEG recording. So right here, I do have a recording done with a waveguard net cap, and I can adjust the scale. And here I have my regular EEG channels. I can re-references. So the default reference is usually done on the position CZ for the caps. So we can leave the reference on CZ, then it would look like this. And then you can already see here that I have an overview over all the segments that were created during the recording process. So that's what we usually do. I start recording with some demo data, just so you can see that the process is quite easy. So let's just say I'm recording EEG, and I want to, oh no, sorry. Sorry for the playback, I can't do the annotations, I'm sorry guys. Anyways, we just have to start recording and do the annotations. During the recording, that's at least what we are aiming for, to save work afterwards, but you can always later on edit the length of the segments or anything in this view. Let's see if this works. Yep. Okay. So we have different segments that we can look at in the EEG recording here. And then we can create brain maps of these segments if we want to. So we can just go to the tab that's called brain maps, and I'm just always double checking that you are seeing the right thing. So in this case, we already have some brain maps. So I can now add a panel to create brain maps. And here on top, I can select the segment that I want the brain maps of. So let's say I want eyes closed segment, and I want to have just the power spectrum of the EEG. And then it will create brain maps that show me the power spectrum of the EEG. Seems like there is one channel that is suspicious for artifacts. So like P7 seems to be something where the recording was not done properly. So this is why it keeps showing up like this. I could also add another brain map panel that, for example, shows Z-scores if I want to. They are automatically adjusted for age and sex. So depending on what I set up for the patient, it is already adjusted for that. And for example, here it shows me the excessive theta. And I can add these maps also to report if I want to. And to generate the automatic report, I can do this from the overview page with one click. It's very simple. So I want to pick one example that I found where I think the brain maps can be interesting to get a better understanding of the localization of certain EEG patterns. So for example, here I have a patient with traumatic brain injury. And here I saw during the recording some slowings. So I made a segment that says slowing, and now I can jump to the segment. And here I saw that there are some slowings. And of course, with some experience, I can also just look at the channels and then figure out if this is something interesting. But with the brain map, it makes it very easy because now I have defined a segment over the slowing part. And if I now go, for example, select brain maps of the, just give a second. So here, for example, I have the slowing segment already selected, and now I can see that there is, or now I can see the location of the excessive theta here and here, so I can localize the slowing more easily and more understandably, and not have to work with the raw EEG only. So this is something that you know, we can use brain maps for diagnostics, not depending on neurofeedback at all. And if I want to add this, for example, to the report to print out for the patient, then I can just add it to the report, and then it is here, and I can create a report and then have this brain map pointed out. So I think this is quite convenient and easy. And as for the neurofeedback, it's actually also quite similar. You can then pick a protocol if you go to the neurofeedback option of the BrainAssistant and have your EEG running. As I said, usually we have individual position neurofeedback, so you pick from a pre-selection of protocols. These are similar to the ones I showed you, so you can pick the protocol accordingly. We also put some training goals here with the protocol, so you can say, okay, I want a protocol that is good to increase focus, for example. Then we will have a selection of protocols that are usually used to increase focus. All the protocols that we present in our default settings are usually backed by some research, at least in the very tiny field of neurofeedback, the research that we have. We selected protocols that are usually at least somewhat proven, or at least somewhat reliable, and not something very crazy that we just came up with ourselves.